We look at the sun every day and yet we do not really see it. Its glare blinds our eyes, its heat burns our skin, but its true nature remains hidden behind that golden surface. No spacecraft has ever descended into its fire. No human eye has witnessed its core. And still, we know. We know that deep within that blinding sphere, matter is crushed under the weight of gravity, fusing atoms into light itself. How can we know something we can never touch? Long before telescopes, humanity watched the sun rise and set with reverence. It was a god, a giver, a destroyer, the heart of myths. Temples faced its path, prayers followed its warmth. Yet curiosity grew. What is that fire in the sky? Could it be earthly flame or something greater? Even before we understood atoms, we sensed that its brilliance came from a realm beyond imagination. Centuries later, the gods gave way to questions. Galileo turned his telescope toward the sun and saw imperfection, spots moving across its surface. Newton showed that sunlight could be broken into colors, a hidden code of nature. The sun was no longer divine, it was a mystery written in light. And we began to read. When we look at the sun, every photon that reaches us carries a secret message from within. It tells us about temperature, movement, and composition. Through spectroscopy, scientists discovered that sunlight is not just white, it is layered with countless signatures of atoms. In those lines, we found the fingerprints of hydrogen and helium, and even discovered an element unknown on Earth, helium, first seen in the sun's spectrum. Light became our messenger across 150 million kilometers of emptiness. But light alone was not enough. The sun trembles, sings, and breathes. Its surface ripples with waves, each vibration echoing from its hidden layers. By listening to these oscillations, helioseismology, astronomers map the unseen interior as if placing a stethoscope on the star's chest. From the rhythm of its pulses, they learn its density, temperature, and flow. The sun has a heartbeat and we have learned to hear it. Still, the most direct whisper from the sun does not come as light or sound, but as something far more elusive, neutrinos. Billions of them pass through your body each second, born in the nuclear furnace of the sun's heart. For decades, scientists built giant underground detectors, vast domes of pure water and light sensors, waiting for these ghostly visitors. When they finally captured them, the message was clear. The sun's core is alive, forging light through fusion exactly as theory foretold. Yet we wanted to come closer. Spacecraft like SOHO, Solar Orbiter, and Parker Solar Probe dared to approach the inferno, each mission flying nearer than any before. They recorded magnetic storms, solar winds, and the blistering corona that extends millions of kilometers into space. These explorers gave us data, real, tangible proof, that our models of the sun's energy and motion are true. Every image they send back is a triumph of both technology and imagination. No one will ever build a laboratory inside the sun, but in equations we already have. Physicists simulate the crushing pressure and searing heat, calculating how protons merge to form helium, releasing light. Every observation, spectra, vibrations, neutrinos, probes, fits together into one grand model. Through reason and evidence, we have turned imagination into understanding. The human mind has entered where no spacecraft can survive. To know the sun is to know ourselves. Its atoms birth the elements that make our bodies. Its energy drives our weather, our crops, our days and nights. We exist because fusion continues in that blazing heart. And the same laws that govern its fire govern the spark in our cells, the electricity in our thoughts. In learning about the sun, we have discovered the unity of the universe, that the fire within it and the fire within us are one. So when we ask, how do we know what happens inside the sun? The answer is not a single discovery, it is the story of curiosity itself. We know because we refuse to accept mystery as the end. Because we listen to light, to waves, to particles, and to silence. Because we built instruments that became extensions of our senses, and minds that reached beyond sight. The sun never spoke, but we learned its language. Long before science, before numbers and telescopes, the sun was the first and greatest mystery. To the earliest people, it was not just a star, it was life itself. Its rising meant survival, its absence meant fear. The sun fed their crops, warmed their bodies, and lit their world. When it vanished beyond the horizon, it felt like death, and when it returned, it was rebirth. It was only natural to worship the source of all warmth, all hope, and all beginnings. Every civilization gave the sun a name, a face, a soul. In Egypt, it was Ra, sailing across the heavens in his golden boat, battling darkness each night to rise again. In Mesopotamia, it was Shamash, the all-seeing eye of justice. To the Aztecs, Tonatiuh demanded sacrifice to keep the universe alive. And in Japan, Amaterasu, the radiant goddess, hid in her cave and plunged the world into darkness, until the other gods lured her out, restoring light. Through every myth, humanity spoke the same truth, that light and life are inseparable. Even within these myths, curiosity began to stir. Priests who worshipped the sun also watched it carefully, recording its movements, marking solstices, predicting eclipses. In ancient Stonehenge and the pyramids of Egypt, architecture aligned perfectly with the sun's path. They had no telescopes, yet they built calendars from light, measured time by shadows, and began to understand that the sun's journey was not random but ordered. They were still worshippers, but already they were becoming scientists. Then came the Greeks, who dared to ask why. Philosophers like Anaxagoras proposed that the sun was not a god, but a fiery rock, vast, distant, and shining by its own light. For this idea he was imprisoned, accused of heresy. But a seed had been planted. From myth grew philosophy, and from philosophy science. The sun was beginning to step down from its throne in heaven, not to lose its greatness but to reveal its truth. As centuries passed, thinkers like Aristarchus imagined that the earth might move around the sun, a radical thought centuries ahead of its time. Others, like Ptolemy, built complex models with the earth at the center, explaining celestial motion with circles upon circles. Though imperfect, these early models showed something extraordinary, that the heavens could be described by mathematics. It was the first time humanity used reason to chase what once belonged only to gods. And yet, after the brilliance of Greece, there came centuries of silence. Superstition and faith once again overshadowed inquiry. To question the heavens was dangerous. To doubt divine perfection was forbidden. The sun remained the symbol of the divine, and those who sought to understand it through reason often paid with their freedom or their lives. But knowledge has a way of surviving in whispers. The Renaissance reignited the flame of curiosity. In the early 1600s, Galileo Galilei lifted his handmade telescope toward the sun, and what he saw changed everything. The perfect celestial body of theology was flawed, alive, dynamic. Dark spots drifted across its surface, proving that the sun rotated, that it was not immutable, not divine perfection, but a star obeying natural laws. The sun became not a god but a phenomenon, and for the first time humanity began to see it as part of the universe, not above it. But revelation came with risk. Galileo's discoveries defied centuries of doctrine, challenging the notion that Earth and humanity were the center of creation. He was condemned, forced to recant, yet his vision endured. The sun, once untouchable, now stood as the center of the solar system, not of worship but of motion, gravity, and truth. What once was sacred became scientific, and in that transformation we found something even more profound: wonder grounded in reality. And so the journey turned. The sun was no longer the object of prayer, but of study. We began to ask not what does the sun mean, but how does it work? Each culture, each age, added a fragment to the truth, from myth to geometry, from theology to observation. Humanity had stepped out of the temple and into the laboratory. We had replaced reverence with curiosity, yet the awe remained. To understand the sun did not diminish its beauty, it made it infinite. From that moment onward, a new question arose. If we can see only the surface of the sun, how can we uncover what lies beneath? The story of humanity's search had changed. It was no longer about gods and myths, but about decoding the unseen. Spectroscopes, telescopes, satellites, and mathematics would become our tools. The sun was no longer just an object in the sky, it was a laboratory of the universe itself. And so began the modern pursuit: to read the light, to listen to the waves, to follow the particles that carry the truth from its heart. As centuries passed, our eyes sharpened and our instruments grew precise. We learned to break sunlight into its hidden colors and to read the code within. The next chapter of this journey would not be written in myth or fear, but in light itself. By the middle of the 19th century, humanity had learned to question everything, but the sun still held its secrets. We could chart its movement, measure its size, feel its heat, but not know what it was made of. The human eye saw only brightness, but science was about to build a new kind of vision, one that could see within light itself. That was the beginning of spectroscopy, the art of reading the language of light. Every beam of light is a messenger carrying coded information. When it passes through a prism or a diffraction grating, it separates into its constituent colors, a spectrum. At first, this rainbow seemed continuous, flawless. But in 1802, William Hyde Wollaston noticed something strange, dark gaps slicing through the colors. Later, Joseph von Fraunhofer mapped hundreds of these mysterious lines with precision. He didn't know what they meant, but he had just drawn the sun's DNA. Decades later, two German scientists, Gustav Kirchhoff and Robert Bunsen, discovered that every element, when heated, emits light at specific wavelengths. Hydrogen, sodium, iron, all produced unique spectral patterns. When they compared these lines to those seen in sunlight, the puzzle clicked into place. The dark lines weren't imperfections, they were signatures. They showed which elements were present in the sun's atmosphere. For the first time, we knew what stars were made of. Then, something extraordinary happened. During a solar eclipse in 1868, astronomers observed the sun's spectrum through telescopes fitted with prisms. Among the known lines appeared one that matched no earthly element. It was a new fingerprint, something not found on our planet. They named it helium, after Helios, the Greek god of the sun. Only decades later was helium finally discovered on Earth, proving the power of spectral vision. Humanity had found a new element by reading sunlight. Spectroscopy did more than reveal composition. It measured motion and temperature. The color of light shifts with heat. Hotter gases glow bluer, cooler ones redder. By comparing intensities and wavelengths, astronomers could now calculate the sun's surface temperature with precision, about 5,800 Kelvin. And with the Doppler effect, they could tell when parts of the sun were moving toward or away from us, like the changing pitch of a siren. The sun's light had become both thermometer and clock. The Doppler principle transformed astronomy. Every spectral line carries motion within it. If the source moves toward us, its light shifts toward blue, if away, toward red. By measuring this displacement, scientists saw that the sun's surface rotates faster at the equator than at the poles. They even detected oscillations, magnetic flows, and storms through minute variations in the lines. From pure color, we extracted movement, speed, and rhythm. Light became motion written in mathematics. At first glance, a spectrum looks like art, ribbons of color and shadow. But beneath that beauty lies pure mathematics. Each line corresponds to electrons jumping between atomic energy levels, obeying quantum rules of probability and symmetry. These transitions release photons of precise energies, forming patterns that can be described by equations alone. What once seemed mystical was, in fact, a cosmic arithmetic, a universe that writes itself in numbers and glows when we read them. By the late 19th century, spectroscopy had revealed the sun's full composition. About 74% hydrogen, 24% helium, and traces of oxygen, carbon, neon, and iron. Each element's presence was marked by its signature lines, tiny scars across the solar rainbow. It was astonishing. The same elements found on Earth were also in the stars. We were made of the same matter as the sun itself. The barrier between heaven and earth had dissolved in a spectrum. Spectroscopy united art and logic. It turned color into data, beauty into understanding. Each spectral line is a conversation between energy and matter, telling us how the universe behaves when no one is watching. Through this method, astronomers learned that every star, every galaxy, every nebula emits a unique voice, a frequency of its own. By collecting their light, we can map not only the composition of the cosmos but its story through time. This revolution in perception transformed astronomy into astrophysics. No longer did we just watch the heavens, we measured them. By reading spectra, we could estimate stellar age, surface gravity, even chemical evolution. Spectroscopy turned light into a diagnostic tool, a way to explore the unreachable. And at its heart was the sun, the first star whose code we cracked. From its light, we learned how to read the universe. When we gaze at the sun now, we no longer see a blank glare. We see a conversation billions of years old, written in frequencies too fine for the eye but clear to the mind. Spectroscopy is our translation tool, our bridge between silence and understanding. The sun is still distant, still untouchable, yet through its light, it has told us everything we dared to ask. And every photon crossing the void still carries that message. Knowledge is born when we learn to listen to light. But the sun has more to tell than its spectrum alone. Beneath its surface lies a deeper rhythm, a pattern of tremors and vibrations that echo through its fiery body. To uncover those hidden pulses, humanity would learn not only to see the sun, but to listen to it. Light told us what the sun is made of. But light alone could not reveal what lies beneath. The sun has no solid surface to touch, no window into its core. For centuries, we could only imagine what churned inside that radiant sphere. Then, in the 20th century, scientists discovered something extraordinary. The sun is not silent. It vibrates. If we could somehow magnify the sun's surface 1,000-fold, we would see it dance. Millions of tiny ripples rising and falling, like the surface of a boiling ocean. These are acoustic waves, caused by pressure and convection deep within. Each wave echoes through the solar interior, bouncing back and forth, shaping patterns across the surface. They are so subtle that the entire sun rises and falls by only a few meters, yet their rhythm carries the secrets of its inner structure. We cannot hear the sun in the usual sense. Its sound waves never travel through the vacuum of space. But telescopes can detect their effect. Minute oscillations in brightness and motion on the surface. With sensitive instruments, we record the Doppler shifts of these movements, transforming them into frequencies that our ears can understand. If you could hear it, the sun would hum like a colossal organ, its tones resonating through millions of harmonics. In the 1960s, scientists first noticed rhythmic oscillations in the sun's surface, small but consistent. By the 1970s, the field of helioseismology was born. Using networks of observatories around the world, astronomers tracked these vibrations continuously, day and night, building a complete map of the sun's internal symphony. It was as if humanity had placed a stethoscope against the heart of a star. Every sound wave probes a different depth. High-frequency waves skim the surface, while low-frequency ones dive deeper, reflecting off layers near the core. By measuring the time and pattern of these echoes, scientists can reconstruct the sun's interior, temperature, density, even rotation. It's the same principle doctors use in ultrasound imaging, or how bats use echolocation to navigate the dark. Except here, the patient is a star 1.4 million kilometers wide. Helioseismology revealed that the sun doesn't rotate like a solid sphere. The equator spins faster, about once every 25 days, while the poles take around 35. This differential rotation twists and tangles the sun's magnetic field, fueling flares and coronal mass ejections. It was a stunning realization. The sun's heartbeat and its storms were part of the same rhythm. Motion turned into magnetism. Through these vibrations, scientists confirmed the sun's layered anatomy. The core where nuclear fusion ignites. The radiative zone where energy diffuses slowly outward. The convective zone, where boiling plasma rises and sinks like a cosmic tide. Helioseismology mapped each transition, proving theoretical models that had existed only on paper. It transformed equations into a living structure. The sun was no longer abstract but tangible through its song. Beyond temperature and structure, helioseismology uncovered vast meridional flows, rivers of plasma moving from the equator toward the poles and back again. These currents carry magnetic fields across the sun's body, influencing the 11-year solar cycle that governs sunspots and flares. In the sun's vibrations, scientists could sense the slow breathing of its magnetism, an invisible heartbeat that shapes space weather and even touches Earth. Each oscillation lasts minutes, but together they form a cosmic metronome, a measure of stellar time. By tracking how the sun's vibrations change, scientists can detect long-term variations in its energy output and magnetic cycles. Even slight shifts in its frequency reveal evolving conditions deep inside, long before we see any change on the surface. It's as though the sun whispers warnings of its moods and we've learned to listen. Helioseismology opened the door to astroseismology, listening to other stars. By measuring subtle flickers in distant starlight, astronomers can now hear vibrations in suns light years away. From these ripples, they estimate stellar ages, densities, and core compositions. The technique born from our own star has become a universal language of sound, a symphony of spheres playing across the galaxy. To listen to the sun is to witness science at its most poetic. We do not simply observe, we translate vibrations into knowledge. What once was myth has become measurement, and what once was silence has become song. Helioseismology reminds us that the universe is not still, it sings constantly. We just needed to invent the ears to hear it. Through light we saw the sun. Through sound we felt its heartbeat. But one question still burned: how could we prove that its core truly burns with fusion? That all this vibration, all this light, comes from atoms merging into new ones? The answer would come from something invisible, almost impossible to detect. Tiny particles born in the heart of the sun itself. Light showed us what the sun is made of. Helioseismology let us feel its vibrations. But both of these senses stop at its surface, the sun's outer 0.01%. Everything beneath remains hidden, buried beneath millions of kilometers of burning plasma. To truly know the sun, we had to find something that could escape directly from its core, something that carries the signature of nuclear fire itself. And nature had already provided it, the neutrino. A neutrino is the universe's most elusive traveler, a nearly massless particle, smaller than atoms, that moves at almost the speed of light. It has no electric charge, barely interacts with matter, and passes through everything, planets, stars, even you, as though nothing were there. Every second, billions of solar neutrinos pass through your body, through the Earth, through every ocean and mountain. They are ghosts of creation, silent, unstoppable messengers from the sun's core. In the sun's core, where temperatures reach 15 million degrees and pressures are immense, hydrogen atoms collide and fuse into helium. This process, nuclear fusion, releases energy that powers sunlight. But fusion also releases neutrinos, each one escaping almost instantly. While light may take thousands of years to reach the surface, neutrinos leave the sun's heart and arrive at Earth in just 8 minutes. They are the most direct evidence of what happens inside. But how can you detect a particle that passes through almost everything? Imagine trying to catch a single snowflake in a hurricane, blindfolded, with a net made of air. That was the challenge scientists faced. To detect even one neutrino, they needed enormous detectors, buried deep underground to block cosmic rays and noise. They built these experiments in old mines, mountains, and caverns, turning the Earth itself into a shield. In the 1960s, physicist Raymond Davis Jr. led one of the first great neutrino experiments, deep in the Homestake mine in South Dakota. He filled a giant tank with 600 tons of cleaning fluid rich in chlorine atoms. The hope: when a solar neutrino hit a chlorine nucleus, it would transform it into a new element, argon. By counting those rare argon atoms, he could count neutrinos from the sun. It worked, but not as expected. He detected only a fraction of what theory predicted. This mystery became known as the solar neutrino problem. According to fusion theory, the sun should emit a specific number of neutrinos. Yet detectors around the world measured only about 1/3 of that. Was the experiment wrong? Was the sun's core cooler than we thought? Or had we misunderstood the laws of physics themselves? For decades, the question lingered, a quiet challenge to everything we thought we knew about stars. To solve the puzzle, scientists built even more sensitive detectors. In Japan, the Kamiokande experiment used tanks of pure water lined with thousands of photomultiplier tubes, devices so sensitive they could detect a single photon of light. When a neutrino struck a water molecule, it produced a faint flash called Cherenkov radiation, a bluish glow. By recording these flashes, scientists could not only detect neutrinos but also trace their direction, back to the sun. When Kamiokande turned its gaze to the heavens, it saw them, real solar neutrinos streaming from the sun exactly as predicted. It confirmed that fusion was indeed happening in the core. We had, for the first time, touched the sun not with eyes or ears, but with the language of physics itself. Yet, the numbers were still lower than theory demanded. The mystery deepened. The sun was producing the expected energy, but not the expected neutrinos. The answer came from an even deeper truth: neutrinos are not constant. They change form as they travel. There are three flavors: electron, muon, and tau neutrinos, and the sun produces mostly electron neutrinos. But as they journey through space, they oscillate between these forms. Our detectors on Earth, sensitive only to electron neutrinos, were missing the others. The problem wasn't the sun, it was our limited vision. In 2001, the Sudbury Neutrino Observatory in Canada solved the riddle. Using heavy water whose hydrogen atoms contain an extra neutron, it could detect all three neutrino types. When the data came in, the total matched perfectly with theoretical predictions. The missing neutrinos weren't missing at all, they had merely changed identity on their way to Earth. It was one of the greatest confirmations in modern physics. Fusion burns exactly as our equations foretold. For the first time, we had direct proof of what happens inside the sun's heart. Not a reflection of light, not a vibration of sound, but a whisper from the very core, untouched, unaltered. Each neutrino that reached Earth had been born in a thermonuclear collision millions of years after the sun itself formed. Every detection was a message across time and matter, a tiny handshake between humanity and a star. In the deepest silence of Earth's crust, buried kilometers below rock and soil, scientists learned to hear the quietest message in the cosmos. It took decades of patience and faith to catch what could not be seen. The neutrino taught us that truth sometimes hides not in brilliance, but in stillness, in the faintest signal carried across eternity. We had finally touched the sun, not through sight or sound, but through understanding itself. The discovery of solar neutrinos changed everything. If we can detect particles from the heart of our own star, we can detect them from exploding supernovae, black holes, and distant galaxies. A new field, neutrino astronomy, was born, opening a window not of light but of matter itself. Through neutrinos, the universe began to speak a new language, one that pierces even the densest darkness. We had seen the sun. We had heard it. And now we had touched its heart through physics. But one frontier remained: to reach for it, not metaphorically but physically, to send machines closer than ever before, to taste its winds, to measure its breath. The next step in this journey would belong not to theory but to engineering. The age of solar exploration had begun. For centuries the sun was an unreachable dream, too bright, too hot, too close to the edge of destruction. But humanity has never been content with distant admiration. After learning to see its light, to hear its heartbeat, and to read its particles, we decided to go there. To send our machines into the fire itself. To look directly into the star that gave us life. In 1995, NASA and the European Space Agency launched SOHO, the Solar and Heliospheric Observatory. It took its position at a gravitational balance point between Earth and Sunday, January 5 million kilometers away. There, suspended between two gravities, SOHO became our constant sun watcher. Its instruments recorded everything: temperature maps, solar winds, magnetic fields, and the blazing corona that stretches millions of kilometers into space. For the first time, we saw the sun as a living machine of energy and motion. SOHO's greatest gift was its eye for the unseen. Using ultraviolet and extreme ultraviolet cameras, it captured phenomena no human eye had ever witnessed. Coronal loops, erupting prominences, magnetic storms spanning entire hemispheres. It revealed that the sun's outer atmosphere, the corona, was millions of degrees hotter than its surface, a mystery that still defies complete explanation. SOHO showed us a sun of contradictions, order and chaos, silence and eruption woven together. Before SOHO, we knew the sun emitted a constant flow of charged particles called the solar wind, but its source remained a mystery. SOHO measured it directly, showing how streams of plasma escape along open magnetic field lines from the corona. These winds shape Earth's magnetosphere, ignite auroras, and sometimes wreak havoc on our technology. For the first time, we saw the sun not as a distant light, but as a force that touches our world every day. For almost 3 decades, SOHO has watched the sun without pause, becoming the longest-running solar observer in history. It captured more than 40,000 flares and over 4,000 comets passing near the Sun. Its data fed the foundation for modern solar models, confirming that beneath its blinding surface, the Sun behaves exactly as our theories of fusion and magnetism predict. SOHO became not just a mission but a memory, a permanent eye that never blinks. Then came the mission that rewrote the definition of courage, the Parker Solar Probe. Launched in 2018, it was designed to fly closer to the Sun than any object in history. Protected by a heat shield that withstands temperatures of 400 degrees Celsius, Parker dives through the Sun's outer atmosphere, sampling the very plasma that streams past us as solar wind. Each pass brings it closer, now within just 6 million kilometers of the surface, where no human instrument has ever survived. As Parker flies through the corona, its sensors record the magnetic fields and charged particles that shape the Sun's breath. It detects turbulence where plasma and magnetism intertwine, where waves of energy accelerate particles to astonishing speeds. For the first time, we see the solar wind not as a smooth flow, but as a storm of structures, eddies and switchbacks, magnetic currents that whip back toward the Sun like cosmic whiplash. In 2021, Parker achieved what once seemed impossible. It entered the Sun's atmosphere. For the first time in history, a human-made object had touched a star. The probe flew through a region where the solar wind is born, where magnetic fields snap and release their energy into space. It confirmed models that had existed only on paper for decades, showing that the corona is structured and layered, not uniform as once believed. While Parker dives in, the Solar Orbiter, launched in 2020 by ESA and NASA, takes a broader view. Orbiting the Sun closer than Mercury, it carries 10 instruments that both observe and measure, capturing high-resolution images while sampling the particles that fly past it. Its unique path will tilt over time, allowing humanity to see the Sun's poles for the first time, a region crucial to understanding the magnetic cycle. Solar Orbiter revealed the Sun's surface in unprecedented detail. It found tiny magnetic threads and mini-flares that release energy thousands of times per second, micro-explosions too small to see from Earth, yet collectively powerful enough to heat the corona. These observations helped confirm long-standing theories that small-scale magnetism, not giant flares alone, is the engine of solar heat. In its images, we saw the Sun not as a sphere of flame, but as a woven tapestry of magnetic threads. The combined data from SOHO, Parker, and Solar Orbiter painted a consistent portrait of the Sun. The temperature gradient, the rotation profile, the flows predicted by helioseismology, all matched observations from space. We now know that the Sun's outer layers are driven by a delicate balance of pressure, gravity, and magnetic tension. Every mission added a piece to the same puzzle, proof that our understanding of the star is not a dream but a science rooted in data. Each mission teaches us more than physics. They remind us that knowledge requires risk, that to understand the light we must step into its path. The Sun feeds our climate, powers our technology, and still threatens our fragile systems with its storms. By studying it up close, we learn not only about a star, but about our own survival and place within its reach. The journey from SOHO to Parker and Solar Orbiter is more than a story of machines, it's a story of faith in human reason. We built instruments that sail through fire to confirm what our minds imagined. We proved that understanding is not a luxury of distance, but a product of courage. Our eyes now see what once belonged only to gods. We are no longer children of light. We are its listeners, its engineers, its witnesses. Now, after decades of data and light, a new question arises: what can we model from all this? If our theories match reality, can we simulate the Sun entirely, its energy, pressure, and motion, within a computer's mind? The next frontier lies not in space but in calculation. The Sun that we see in the sky will soon be reborn in mathematics, a digital star built from knowledge and numbers. For centuries we looked at the Sun. Now we have learned to rebuild it, inside mathematics. No spacecraft can survive its inferno, no probe can pierce its core, yet on chalkboards and computer screens, scientists construct a miniature Sun from symbols, numbers, and laws. It is not made of fire but of logic. And still, it burns with truth. Every model begins with a balance. Gravity pulls inward, trying to crush the star. Pressure pushes outward, born from fusion's fury. If one wins, the star collapses or explodes. If both remain in harmony, it lives for billions of years. This delicate equation, pressure equals gravity, is the heartbeat of every star and the foundation of solar theory. Inside this model, temperature and density are written not in degrees but in formulas. At the sun's core, numbers replace sensation: 15 million Kelvin, 150 billion atmospheres. Equations describe how photons born in the center wander outward, bouncing through plasma for thousands of years before escaping as sunlight. Mathematics becomes time itself, each variable a story of heat, confinement, and release. To capture the sun, scientists divided into zones: core, radiative layer, convective layer, photosphere. Each obeys a different set of equations. Energy transport by radiation, turbulent motion by convection, hydrostatic balance, and opacity by quantum physics. These layers are stitched together like chapters of a single equation, a living document of plasma and pressure. But a model is only alive when it agrees with reality. So scientists test their equations against every clue the universe offers: spectra of sunlight, vibrations on the surface, and ghostly streams of neutrinos from the core. If the theory predicts them all correctly, the model stands. If one piece fails, the math must be rewritten. Thus, the sun we know is not imagined, it is verified, cross-checked, and confirmed by nature herself. For decades, our models predicted more neutrinos than detectors found. It was a cosmic discrepancy, a whisper that something in our equations was missing. Then physics evolved. Neutrinos were discovered to change flavor as they traveled, transforming from one type to another. With this revelation, the models aligned perfectly with observation. Mathematics had been corrected by reality itself, and the invisible had proven our understanding true. In the 21st century, laboratories no longer hold fire, they hold computation. Supercomputers simulate billions of particles interacting, reproducing nuclear fusion, turbulence, and magnetic storms. The equations once scribbled on paper now live in digital universes where we can watch a virtual sun evolve in seconds. These simulations reveal things no telescope can: how magnetic fields twist, how solar cycles breathe, how chaos hides within order. When the numbers settle and the code stabilizes, the digital sun glows steadily, balanced between gravity and fusion, chaos and symmetry. In that moment, a truth becomes clear. The laws that govern a star are the same that govern everything. From the collapse of a sunspot to the heartbeat of a cell, balance sustains all life and all matter. The equations of the sun are the equations of existence. Beneath layers of complexity lies a single principle: energy seeks balance. In stars, that balance shines as light. In humans, it becomes curiosity, intellect, and the pursuit of understanding. Our equations are reflections of ourselves, fragile, persistent, and endlessly searching for harmony. We built the sun from mathematics not to imitate creation, but to glimpse the order within chaos. And yet, even with perfect equations, something remains unsolved. Why does the universe choose to obey mathematics so precisely? Why can our minds, small sparks of consciousness, recreate the structure of a star? Perhaps that too is part of the mystery, that in understanding the sun, we are understanding the universe's reflection in ourselves. The equations are not the end of wonder, they are its continuation. For thousands of years, humanity has watched the sun rise, never realizing that we were also watching a reflection of our own story. We thought we were learning about the heavens, but each discovery, each equation, each spark of curiosity was, in truth, a mirror, showing us what it means to think, to question, to dream. The sun is more than a star. It is a symbol of awareness itself, the visible face of our invisible search for meaning. The light that travels from the sun takes 8 minutes to reach Earth, but in that time, it has already crossed the bridge between physics and philosophy. Because when that light strikes our eyes, it becomes thought. It transforms from energy into perception, from photons into awareness. In the same instant that sunlight illuminates the world, it also illuminates the mind. The outer light becomes inner light. Science is not the opposite of faith, it is its evolution. For the ancient priest who prayed to the dawn and the physicist who measures solar fusion are bound by the same instinct: wonder. One saw the sun as divine presence, the other sees divinity in its precision. Knowledge did not destroy faith, it redefined it, turning belief into understanding and reverence into curiosity. The same fire burns in both, the fire of seeking truth. Curiosity is humanity's oldest prayer. Every measurement of light, every formula, every question whispered into the dark sky is an act of devotion. Devotion to knowledge, to truth, to the cosmos itself. We chase the sun not because we hope to possess it, but because something within us needs to understand. The same curiosity that once built temples now builds telescopes. And through that continuity, we remain children of light. Light is both messenger and metaphor. In science, it reveals atoms and energies. In spirit, it stands for truth and consciousness. When we decode its spectrum, we decode not only the sun but the structure of understanding itself. Perhaps that is why we are drawn to it, because light behaves like thought, invisible until it meets something that can reflect it. The sun shines, we reflect. Inside the sun, chaos reigns, storms of plasma, violent eruptions, and magnetic battles. Yet from that chaos comes perfect order, a steady glow that sustains all life. So it is with us. Within the storms of the human mind, fear, doubt, desire, arises the light of understanding. We are fragments of that same cosmic pattern, balancing fire and peace. Every sunrise repeats the same lesson: renewal. No matter how long the night, the light returns, not because of faith but because of law. And yet that law feels sacred. The sun teaches us resilience, constancy, and patience. Its rhythm reminds us that darkness is never final, it is only the waiting side of light. Through the sun we discovered unity. Its elements are our elements. Its atoms forge the ones in our blood and bones. When we study the sun, we are not looking at something foreign, we are looking at our origin. We are children of its radiation, heirs of its fusion. We are, in the most literal sense, sunlight made conscious. With understanding comes responsibility. The same knowledge that allows us to harness the sun's power can also harm the balance it created. To study the sun is to be reminded that light, though infinite, can be fragile in our hands. Science gives us tools, wisdom decides how to use them. The sun is eternal only if we learn humility in its glow. In the end, the journey that began with worship and evolved into science leads us back to the same truth. We study the sun not merely to know the universe, but to understand what makes us human. Its light shows us our limits and our potential. Its energy burns in every thought, every heartbeat, every act of wonder. The sun is both our origin and our mirror, its light the reflection of our own becoming. And so, after all the centuries of watching, measuring, and dreaming, the truth feels almost poetic. We have not conquered the sun, we have joined its story. For the light that shines upon us is the same light that lives within us, and that, perhaps, is the most beautiful discovery of all. Everything we are was born in stars. The calcium in our bones, the iron in our blood, the carbon that shapes our thoughts. Each atom once burned in a furnace of light. When those ancient suns died, they scattered their ashes across the cosmos. From that stardust, the earth formed. And from earth came us, living echoes of long-extinguished stars, carrying their fire forward in flesh and memory. The same nuclear fire that fuels the sun still burns in us, not as flame but as metabolism, warmth, thought. Every heartbeat is powered by energy that began billions of years ago in stellar cores. We inhale what the stars exhaled. To live is to continue the reaction that began at the dawn of the universe. We are not separate from the cosmos. We are its continuation. Now, after centuries of searching, we know what makes the sun shine, and yet the mystery feels even deeper. Science has not diminished wonder, it has refined it. We no longer look up seeking gods, we look inward and find galaxies. The boundary between knowledge and awe dissolves, leaving only quiet gratitude for being able to see it all. Every sunrise is an ancient dialogue continuing still, the universe speaking to itself through us. Each photon that touches our skin is a message from the beginning of time saying, "You belong here." Our science, our art, our love, all are forms of light trying to find their way back to the source. We are not observers of the cosmos, we are its consciousness. We are stardust illuminated by starlight. The universe became aware of itself through our eyes, our questions, our fragile brilliance. We have never been inside the sun. But the sun has always been inside us, burning quietly in our hearts, in our thoughts, in every act of wonder that keeps the darkness away.